Hello everyone, and welcome to the A3 webinar series. Today's webinar is entitled 3 Pillars of Successful Robotic Material Removal. Thanks for joining us today. My name is Clarissa Carvalho, and I'm the Marketing Specialist for the Association for Advancing Automation. I'll be serving as your moderator today. Attendees viewing this webinar are in listen-only mode, which means that you are muted. If you have questions during the webinar, please submit them in the question panel at the right of your screen. We will try to address as many questions as we can at the end of the program. If your question is not addressed during the webinar, we will respond via email. This webinar will be recorded, and a link will be sent to you in the next 24 hours. If you're joining us for the first time or after a long while, the Association for Advancing Automation, also known as A3, is the umbrella association for the RIA, AIA, MCMA, and A3 Mexico. These 4 associations combined represent almost 1,300 automation manufacturers, component suppliers, system integrators, end users, research groups, and consulting firms from throughout the world that are driving automation forward. We are hosting our first virtual conference next week, AIA Vision Week. During this event, we have a whole day scheduled solely around the topic of vision and robots. Since you have joined us today for this robotic material removal webinar, we encourage you to register for the May 22nd Vision and Robots session. Participation is free, and anyone interested in these technologies is encouraged to register at visiononline.org. I would like to thank the sponsor of today's webinar, ATI Industrial Automation, is a world-leading engineering-based developer of robotic accessories and robot arm tooling, including material removal tools, automatic tool changers, multi-axis force, torque sensing systems, utility couplers, robotic collision sensors, manual tool changers, and compliance devices. Their robot end effector products are found in thousands of successful applications around the world. Since 1989, their team of mechanical, electrical, and software engineers have been developing cost-effective, state-of-the-art end effector products and solutions that improve robotic productivity. Thank you to ATI for sharing their time and expertise with us today. I'd like to introduce our presenters of today's webinar. Dan Merritt began working at ATI Industrial Automation in 2004 as an applications engineer, where he worked extensively with ATI's robotic deburring tools, tool changers, force torque sensors, and other end effector products. He has since become product manager of ATI's Material Removal Product Group, where he directs a diverse engineering team in application development, product design, customer support, and application capability studies. He is motivated to bring new material removal solutions to ATI's rapidly growing customer base. Dan is a graduate of North Carolina State University with a Bachelor of Science in Mechanical Engineering. Sarah Mullins began her 3M career in 2001 after graduating from University of California, Berkeley with a PhD in chemistry. She develops new materials in 3M's corporate research laboratory and started with the Abrasive Systems Division in 2007. Her contributions to ASD include both process development and product development for 3M's Cubitron 2 abrasives. Currently, Sarah is an Abrasive Systems Division Global Application Engineer focused on designing robotic abrasive solutions for grinding, blending, sanding, finishing, and deburring of cast and forged products. Thanks for being with us today, Sarah and Dan, and I'll now hand this webinar over to you.
Great, thanks, Clarissa. Good afternoon, welcome everyone, and thank you so much for joining us today. Our goal for this webinar is to get you excited about opportunities and new capabilities that robotics create for material removal processes. And when we say material removal, we're talking about grinding, sanding, polishing, and deburring type applications. ATI and 3M are co-presenting today because we both share a deep investment in engineering, quality, and responsibility to our customers. Our organizations have complementary competencies that can help make your automation journey easier.
Thanks, Dan, for inviting me to participate today. I'm excited to discuss the possibilities of robotic material removal with you and the attendees.
So today we'd like to frame the content and conversation as three pillars that we see common to robotic material removal applications, which are successful. So represented here, the why, the what, and the how. We're first going to explore the why. How do we identify value and opportunity for automated material removal solutions? And then we're going to explore the what. How do we define requirements and expectations? And then finally, which is my personal favorite part, the how, the technology, the products, the end effectors, how abrasive and process parameters all have to work together for a successful application. So let's jump right into the why. Why is there so much market potential for automated material removal solutions? The biggest driver may seem obvious, but it's safety. I think a lot of us here on this webinar today have heard the 3 Ds of automation: dull, dirty, and dangerous. And I think we would all agree that material removal processes check all of those boxes. And these are issues that result in significant labor challenges. As an example, a heavy casting end user in Ohio reported an average employee turnover for their chipping and grinding operation to be 1 month. And it's hard to fault those employees when they reported losing feeling in their fingers due to the vibration they experienced every day and had to soak their hands in hot water every night just to regain the feeling. That may seem dramatic, but it's not exclusive to that application. In the UK, some high vibration applications have restrictions in place that limit the duration that an operator can use a grinding or sanding tool to just 2 hours per day. That demands a rotational labor force to be able to perform this operation. So it's important to identify that automation offers an opportunity to create safer and better roles to elevate operator jobs to higher value tasks. Sarah, what is 3M's experience when it comes to motivating factors for automating material removal processes?
Well, we see a lot that end users who are interested in automation also want to use the best practices in material removal. They see that they can improve both safety for workers and quality of their parts. And these end users see automated material removal can help them open up operator time to take on new projects. And they're really hungry to understand why automation might be a tool that helps them address their pain points across their plant operation.
Now, as we dig in a little deeper, I think it's common for companies to limit the scope of their return on investment calculations or their business cases to just the capital investment for that automation equipment versus the labor savings they have a tendency to reap. But it's important to make an earnest evaluation of all the costs and all the issues associated with that manual process, and also try to quantify the far-reaching benefits of automation. One example is scrap rate. After implementing a robotic solution, the end user I just mentioned in Ohio estimates approximately $50,000 in savings annually due to scrap reduction alone. That's $50,000 every year that they're no longer literally throwing in the recycle bin. Their workers' compensation claims are down. Their employee turnover rate is down for these roles, and that has reduced costs of recruiting and onboarding and training. The operators who were using those grinders manually are now running the robot and say they'll never go back to running that grinder again. Improved quality output in that process has had a downstream effect where they've been able to reduce the labor for those downstream operations, those follow-up processes. So you can see the benefits of automation extend beyond the obvious, beyond just the robot cell, and can snowball into other processes and other aspects of your business. Sarah, what has 3M learned about the market opportunity for automation in material removal?
Well, it's interesting because even though some industries were sort of the lead users of automation, finding automation is relevant across all industries for material removal. So that includes the heavy industrial grinding examples like you already referenced, to precision finishes required in medical implants, and even to consumer products where aesthetics are most important. For example, your personal electronics, furniture, household appliances. There is a lot of opportunity. And when you think of just sanding alone, We estimate that over 100,000 facilities are doing manual operations today. And at any given moment, someone is considering their readiness for automation.
I would agree, Sarah. ATI sees the same thing across our customer base. So I hope that now, as we've discussed these potential opportunities and the value they represent, that if you're an end user attending this webinar, you'll be looking for opportunities in your own plants, in your own processes to improve safety and profitability. And if you're an integrator listening in, we hope that you'll see that this market represents a tremendous opportunity space. With that, let's move on to our second pillar and dive into defining what needs to be done.
Okay, so let's dig in a bit here. We want to define what needs to be done from the view of your part. Usually, end users considering automation start with a part that they have been making and selling for a while. So confidence about your readiness for automation really starts with the same three questions you should be asking for your manual operation. We want to step back for a second from the process tab and do a gut check on the changes needed on the incoming part. First, what is the purpose of the abrasive step? Is it to create a certain appearance on the part, like maybe a high polish? Or maybe the part needs changes to dimensions, like removal of a gate or deburring. What is your measure of good? This can be subjective, objective, or both. Subjective criteria we see include creating a consistent scratch pattern to create an aesthetic visual effect, or aligning linear scratches across a part. Objective criteria might be creating a radius edge, something that can be validated with a gauge, or it could be about reducing the number of defects within a given diameter on your surface. And finally, what are your tolerance requirements? In truth, all processes have variability. For your part, is it critical to hit a tight dimensional tolerance target, like in an aerospace component? Or maybe you're making sledgehammers and the size tolerances are more forgiving. The fundamental rules of abrasive processing still apply. So now let's take a moment to look at how that abrasive step fits in with the other components of a robotic cell operation.
Well, whether this is the first robot in the plant or the 100th robot to be installed in the plant, it is important to think about the fundamental automation considerations for any given application. As an example, environmental factors may dictate the type of tool that you use. If we have a potentially explosive environment, we may not be able to use some electric motors and need to use a pneumatic motor. If our plant compressor can't keep up with high flow pneumatic tools, we may need to limit our scope to electric spindles. It could be as simple as how much floor space is available that determines the robot size or the type. We have to consider how the material will enter and exit the robotic process. Is this going to be a manual load station, a conveyor, or a bin or a rack? How are we going to clamp and fixture the parts for processing in a repeatable fashion? Will we require any in-process measurement or inspection? How often do we need to change out our cutting media? Will that be done automatically or manually? Is this going to be a fully custom design, or are we going to use prepackaged solutions? Do I need one robot, or do I need more than one robot? Or maybe multiple tools on one robot using one of those fancy ATI tool changers? There is no correct one answer for any one of these considerations. They're different for every customer's unique situation, and that is going to shape the automation solution accordingly. So now we hope you have an understanding and the importance and scope of defining what needs to be done. So let's dive into exploring how we go about doing it.
Okay, so exploring the how. You've defined what material removal work needs to be done on your part, yet you might not be sure, can it be roboticized? What you see here are 6 example abrasive processes that we have seen successfully automated with robots. from degating and finishing applications common to those medical implants to weld spatter removal in automotive assembly plants. The thing to keep in mind is that each one of these processes existed first as a manual operation. So as you explore the how, involving material removal experts from places like 3M and ATI is a good idea because more than likely, we've seen a robotic version of your manual process. Explore the how also means look beyond replacing human arms with robot arms. How does adding a robot improve the abrasive or material removal processing required for your part? Next in Explore the How is actually defining the process. This means identifying the combination of equipment, abrasive, and process parameters that meets the removal needs for your part. And just like with manual operations, there are multiple process solutions to get the job done. Bringing in a robot does not mean identifying the perfect recipe. A robot brings in repeatability of process conditions, and it stabilizes process parameters. As you can see here, we have a lot of different parameters that can be dialed in. So typically, when we test parts in our robot lab, we will seek to identify several good processing options and to help the end user to understand the trade-offs of different approaches before committing to one path forward. The use of the robot also creates the opportunity to build an equipment setup designed to reach process parameters that bring out optimal abrasive performance. And just to speak to a moment to the product type, the coated 3D, non-woven, and hard tooling abrasive media, each are engineered to a specific purpose and application. The coated abrasive you see there is an abrasive version of like a cutting tool, and it's going to cut fast and quickly and cool. The 3D version is going to have very consistent finish across the life of the abrasive. So that's really important when you're getting down to that, trying to get, say, to a mirror finish. A non-woven has compressibility, conformability in it, so it can fit around contours on a part or defer to shape, and it has abrasive throughout. So again, a very consistent cut. And hard tooling is going to have its specific application in chamfering and deburring, for example. So you can see there are a lot of tools in the toolbox. So again, key takeaway is to bring in material removal expertise in the early stages of exploring automation, because we can help you iterate quickly and identify equipment tweaks that let you narrow in on the most promising process options. Sometimes this means you get to achieve more than you even imagined was possible. For example, a large gate on a cast iron part removed in just seconds and in a single pass of the part across a belt on a back stand. That is enabled by some tweaks in your contact wheel, selection of the right belt, and operating at the desired force. Another example is like if you have a blending and finishing belt sequence on a stainless steel part. When you have each step optimized to cut more efficiently, overall the part is going to run cooler. This extends media life and also prevents more rework to prevents burns on the surface and the need for rework. So what makes this really possible? What ties it together? One key parameter is working in the optimal window of applied forces appropriate to the abrasive media and your part. We know from manual operations that proper force is what makes the abrasive cut without wearing prematurely. So you can think of this as the way a person will naturally lean in to add force to increase cut rate, or back off if they feel the cut is too aggressive. So it's important to consider options to achieve the desirable forces with your robot. Dan, how do we think about this in the robot world?
Well, we know that robots are repeatable and consistent. That's what they do best. But the material removal world is filled with inconsistencies. The starting condition of the parts can vary from one part to the next, from operator to operator, from shift to shift, or even gradually over time as casting or machining equipment might wear. So typically robotic solutions are going to involve some sort of compliance or other means to compensate for all of those potential variations to achieve and maintain that optimal applied force that you're talking about with consistency. Now, the good news is there are several methods by which we can do this. One category is passive force control. These systems may involve pneumatics or springs to be able to set a desired contact force and have a range of motion to compensate for dimensional variability in an open loop system. These are typically independent of the robot, meaning the robot will just follow its programmed path the same way every time, and the device does its thing independent. The second category is active force control. In these systems, the applied force is being measured, and that data is used in a closed loop control method to actively make changes or adjustments automatically based on that feedback. And there's even a few different ways to do this. One way is through the arm, meaning the robot motion is being altered to control the force. For example, the robot speeding up or slowing down its path to change the removal rate, or moving closer to or farther away from a part to achieve that desired result, similar to the way Sarah mentioned a person might lean in or back off. Another type of active force control is around the arm, meaning it's a device independent of the robot arm, which measures the applied force and is able to actuate the tool closer to or farther away from the workpiece automatically to maintain that constant applied force throughout the process. Now, historically, we've just considered active and passive force control, but new technologies and new creative approaches have created a third category of what we refer to as hybrid systems, which can bridge that gap between active and passive. For example, we can take a passive force control device and use robot position data or an accelerometer to know the tool's orientation in space and be able to bias out the weight of that motor or tool and apply a constant force, whether that tool is horizontal or inverted or anywhere in between. Sarah, based on 3M's experience, is any one of these systems better than another?
Well, the short answer is it depends. We see a lot of different setups depending on the part and removal needs. And while there are some similarities within applications, even factors like your specific part shape and the complexity of your contours, or whether the part has a dimensional or aesthetic endpoint, all of these will factor into the selection.
So hopefully now you get a basic understanding of these different categories of force control conceptually, but let's look at examples of how this manifests. What kind of tools and technologies are available? We've already mentioned that there's no one-size-fits-all solution for material removal applications. Instead, I'd ask you to think of the current and emerging technology as a toolbox. You can turn a bolt with a ratchet and a socket, or a hex wrench, or an adjustable wrench, or vice grips in a pinch, but which one you choose is based on the specific need in that situation. Similarly, there might be multiple tool options that can perform a material removal task and achieve that desired finish. But all of those factors we discussed as part of those first two pillars can dictate which is best, which one should we choose for this specific situation. On the left side of the slide are some examples of tools with integrated compliance. meaning the tool motor is built into a compliance device. These integrated compliance tools are typically smaller, lighter weight, allowing for smaller robots or tighter access if necessary. If you look on the very far left of the slide, you'll see a random orbital sanding tool with a purple 3M abrasive media. This is ATI's brand new AOV orbital sander, which features integrated passive compliance, but it can be paired with additional hardware and software and become a hybrid system capable of automatic gravity compensation. On the right half of the slide are a couple of examples of modular systems, which feature the compliance as a flexible platform to be paired with any appropriate material removal tool. The orange tool on the very far right of the slide is a new ATI passive compliance device. It's pneumatically actuated for adjustable passive force control that we've discussed. It also has deflection sensing for process verification and electronics on board to facilitate gravity compensation automatically, as another example of that hybrid system that we talked about earlier. So Sarah, I see some pretty unmistakable 3M logos in the other equipment that's shown on this slide. Perhaps you can tell us about that.
Sure. So this picture here is showing fiber discs grinding down wells, and it highlights the usefulness of a modular approach. The equipment shown here actually has two modules, a force control unit and a motor. And depending on if you are running a 4.5-inch or a 7-inch fiber disc, these will run at different rotational speeds. And this is both for abrasive performance and safety reasons. So having a modular motor brings some flexibility. It can be swapped out as needed when the abrasive disc size is changed. For example, if the robot is working on a different part in a different shift.
So on this slide, we see several examples of tools that incorporate force control. Understand this is certainly not comprehensive. This is the tip of the iceberg of existing technology that's out there and options that are at your disposal. And so you'll see that these are a variety of active and passive force control, integrated and modular. But one thing that's common to all of these that we're looking at is that they're all around the arm solutions. They're independent of the robot. And so I want to take a moment to highlight some through the arm options that we referenced earlier. In these systems, a 6-axis force torque sensor is measuring forces and torques, and that information is being used to change the robot's behavior in real time. On the left is a system where the force sensor is mounted between the robot wrist and a heavy-duty sanding head. During the sanding process, that force torque data is driving decisions to move the robot faster or slower, to move it closer or farther away from the work surface, automatically based on those predefined thresholds. On the right, this is a very unique application where the robot is being controlled manually by an operator with an industrial wireless controller reminiscent of a video game. You'll see the operator is standing safely outside the robot cell in a clean and safer environment. Here, the FT sensor is measuring the forces and feeding that information back to this controller with haptics built into it so the operator can feel when they've made contact with the part. They can feel what they're doing. As they push on the part, the controller pushes back. This particular system is intuitive. The operators, when they first rolled it out, without ever having touched a robot pendant, were able to be up and running and moving the robot around within 20 minutes because of that familiarity with that video game type controller. This application is a wonderful example of a marriage of human skill, experience, and talent with the strength and toughness of an industrial robot. The operator is still able to use those skills built up over years of experience to create tremendous value, but now in a much safer environment. Sarah, can you speak to how 3M or 3M's customers have utilized force sensing?
Yeah, I have two examples actually I'd like to share. First, when you have media that changes size during use, like a unitized wheel, a force torque sensor can be used to create a media touch-off protocol. So basically, within your cell at set intervals, the robot is going to check the diameter, use the force torque sensor to check the diameter of the abrasive. And then based on that position, the program is going to automatically index the teach points. This way, for future parts, the part and abrasive will continue to make the proper contact, and it maximizes the full use of the abrasive. Second example is a force torque sensor can be very helpful when you want to do performance studies for deeper understanding behind process optimization on your part.
Great. So while perhaps we've overwhelmed you with all of these different options, the good news is that your potential toolbox is full of a lot of options now. And companies like ATI and 3M are still investing heavily in new product development to continue to make automation of these material removal processes easier and more approachable than ever. So now that we've dived into every one of these pillars individually, let's take a moment to talk about how we put all of this together. Now, it's not uncommon for people to think that once they've identified an opportunity for automation, that the next step is to just install the system, right? Let's go. But as we've shown today, there's many steps in your automation journey, and ATI and 3M can help along every step of the way. So we encourage you to involve partners like ATI and 3M in all three pillars, in that why, in that what, in that how. ATI and 3M have teams of application engineers dedicated to material removal products and processes. 3M and ATI have robot labs dedicated to proof of concept trials. ATI offers a tool leasing program to allow you to explore capabilities yourself if you prefer.
So we've focused most of the time in this webinar on the steps that build the confidence that you have a material removal step ready for automation. But you can also see that the how box here is larger than what we covered today. It includes many factors that will impact success, such as safety considerations and engineering choices that have practical considerations, like getting your robot reach the equipment, or how to introduce equipment for media change. These may be additional touch points that are a good time to check in on the abrasive step and make sure that everybody understands how that is successful. We think of the proof of concept as that starting point to build the actual process cell. And if you keep your material removal experts engaged in these final steps, we can help troubleshoot or be a reference to how equipment choices make the abrasive process successful, so that your final automation design and installation will deliver value to your company. Thank you.
So our hope is that you've learned a lot today and that you've gotten excited about the possibilities in robotic material removal. What questions can we answer in our remaining time to help you today?
Thanks, Dan and Sarah. To our live attendee listeners, please submit any questions you may have at this time using that questions panel at the right of your screen. Several questions have already been submitted, so Dan and Sarah, here is the first question. Dan, we'll start with you, and then Sarah, you can fill in. Can I use the tools I'm currently using in my manual process with a robot?
Sure, thanks, Clarissa. So we've actually at ATI seen this quite a bit. It's a very logical step to take a tool that's being used manually and find a way to bolt that up to the robot and call it good, right? Let's try that out, right? We're using that tool successful manually, and then why wouldn't it be successful on the robot? And you know, that can work for proof of concept or to generate some ideas, but in our experience, those manual tools are designed for manual processes. They're designed for human being ergonomics. They're designed for human being work environments. There are several things that are unique to a robot operation versus manual. If you think about a grinding or a sanding operation, the person using that tool, their body is in and of itself a vibration isolator. Their arms and their body are absorbing that vibration. And so when we take that same tool and put it on a robot, what's going to happen to that tool? What's going to happen when it doesn't have that isolator built into it? We see premature failure of bearings and motors, which are designed for manual operation instead of robotics. And so robotic tooling is designed with all of those considerations in mind. Does it need to be more robust? Can it be heavier duty? Can it be, even an electric tool? Think about how the way it's plugged into an extension cord on a shop floor. If we take that same extension cord or that same tool cord built into it and we run it up a robot arm, and now those 6 axes are twisting and turning and bending, that cable itself is going to fail. So we have to design every aspect of the tool and the way we interface to it for automation to make sure it's going to survive and we're going to get the most out of it.
So the thing I'd add to that, kind of going back to when I was talking about tweaking your process to get more from the robot, oftentimes we find that the ideal abrasive performance will actually come from positioning the product at angles and speeds that are difficult for a person to maintain, so that, again, that tool is designed to make it easy for a person to operate it. But if you think back to that weld grinding equipment, we actually run that disc at a much shallower angle than we tell manual operators to do, because the robot can hold that very, very, very steady. So that gives higher cut and longer life into the abrasive product. So there's application design reasons as well that you want to utilize the equipment that is designed to be working on a robot.
Thank you, Dan and Sarah. Our next question is likely directed to you, Sarah. Is it possible to check how much of the abrasive is left on the, for example, abrasive belt?
This is a great question. I'll give you 2 answers. First, there are vision companies who are working on this problem, and they want to understand how they can help in abrasive processes be able to give real-time understanding of how much life is left on abrasive media. So people are working on it, but it's a tough problem to do a real-time measurement. So that is really, something for the future. Right now, the way that we advise people is this is where the runoff and the initial measurements after your cell is installed in your facility are really important, because that's when you can, with your exact parts and your exact setup, actually go and run how many parts do you get before you get to the actual end of life. It's something that we really advise people to measure empirically. We are able to, we often will go out when we've been working with a customer in a process and come and attend a couple of weeks after you have it all installed and you've got your hands on that operation, and we'll help you understand where the abrasive is in its life at different points. Depending on what you're using, if you're using like a Trizec belt, one of those 3D belts, we've had customers who have pulled out calipers, and the wear is so even that you can actually make measurements to see the thickness of the belt change. So there are some tricks and tips that we can give you to help create that empirically. But I would just say that the most important thing is it's a question that has to be answered in your application on your part. And we want to help.
Thank you, Sarah. Dan, this one looks like it's for you. Can you provide some examples of around the arm and best case scenarios for this implementation?
Sure, that's a big question because the answer is that's a broad space. So around the arm, ATI's largest installed customer base is utilizing integrated compliance passive force control tools. That's the bulk of our existing product line, and so that's our most broadly installed base. And so if we look at passive compliance around the arm, a lot of customers will come to us and they've identified those challenges. We have a cast part we want to remove the flash on. We have a aluminum extrusion that we have cut, and now we have some burrs that we need to remove. And so every single application, we work with those customers to identify what the needs and requirements and limitations are. So every single one is approached differently because it's likely to be a different result. Every now and again, we do get one that's very familiar, and we can cite those saying, okay, we use this ATI tool. You need to move your robot at approximately this speed, use this cutting media, and these are kind of results that you can expect. But the most common way to go about this, and the best practice, is to have that conversation with us and go through that process, meaning let's look at our different options and then use that proof of concept step to be able to prove out. If you're an integrator, be able to show the customer that part and say, this is what we're capable of. If they're an end user, they can get that part back in their hands, or they can see photos and video and say, yes, this is going to meet our needs. And then usually once we get in the ballpark and we think we've got the appropriate tool, meaning the right compliance range, the right media, abrasive or hard tooling media. And so we get in the ballpark, and then the fun part is tuning those parameters upon installation. And so we get in the ballpark, we get our robot cell, whether it's in a test environment or production, and then we can do things like adjusting the compliance force to really zero in on what is going to give us that best balance of cycle time and throughput and our desired finish and tool or abrasive media life.
Thank you, Dan. This one is a question for both of you. So Dan, we'll start with you and then go to Sarah. What are some of the challenges you face when you use hard tooling with a robot? There's a second part of this question. What strategies are you using to overcome them?
Sure. So hard tooling, what's different about that than some abrasives or brush products is that there is no compliance or forgiveness built into it. It is just that it's a hard tool. And so when you look at the manual process, let's say a die grinder or an air motor driving one of these carbide burrs, that person operating that, they have eyes to be able to locate the part. They have that feedback in their own sense of touch to know when they've made contact, and they can move that tool faster, slower, all those things we discussed earlier in the webinar. Now, when we move to a robot, if we just take a tool with that hard tooling and we put it on that robot without some sort of other input or a force control or compliance device that we discussed, the robot is only going to do what is told. It's only going to go in that one path, that one location. And so unless you can get real consistency on your incoming part quality and what you're trying to do, unless you can locate it and clamp it and hold it in the same exact repeatable position every time, you're inherently going to have some variability. So if we don't have compliance, if we don't have a means for force control, then we stand a chance of that tool not being close enough and not removing enough material. We have a chance of it being too close and digging into the parent material. And so that's when we combat that with the different compliance and force control methods that we outlined in the webinar to try to bridge that gap between the manual process and the robotic process.
Thank you, Dan.
So one thing I'll just add, I'll just add to that, is sometimes we find it's good to ask the question, in fact, what do you need from your part? And sometimes when a customer has been using a hard tool to make a chamfer, and then and that's what they're used to, but when they really reconsider, it's not that they need a chamfer, it was just a way that they had gotten the job done. So if they're just looking to deburr for safety reasons and a radius is okay, this might be an example where we suggest an option of looking at a different media and really making sure that the media is well suited to what your part actually needs, because you don't want to be that's how you're going to get the optimal performance out, is if we've we check in on that gut check, we validate that that hard line is more what you need for your part, and then we can either go forward with a solution like Dan has suggested, or if it isn't needed, we can open up the toolbox a little.
Thanks, Sarah. Our next question looks like it's for Dan. Are the connections going to the end effectors on the outside of the robotic arms ever damaged?
That's a great question. That sounds like an experienced integrator asking that question. Yeah, it's certainly possible. What we have to do in a robotic world, we have to try to make that utility connection, that robot dress pack, as we call it, the cables or the air lines, whatever we have going to that end effector, we have to try to make that as friendly as possible. Now, there's lots of great accessory technologies to make that as friendly as possible, but things can happen in an automated situation. Unexpected environmental issues or something can cause a cable or an airline to get snagged. They can result in damage, and then just overall wear. Sometimes things get twisted around and moved around a lot. What's important when you look at end effector selection or design is that you understand that possibility, even if it's unlikely. And so we have to look at, how do we make sure that if that does happen, it's not going to create a lot of downtime. It's not going to affect our performance of our tool. So, for instance, in a lot of ATI's tool designs, what we'll do is make sure that our air connections or electrical connections are in a position to where if that cable does get pulled on, or someone is well-meaning and they decide to strap it down tightly to the robot arm, and that means it's going to see a lot of strain, that external force isn't going to affect our compliance motion. We have to make sure that we can still, if something like that happens, that we're still going to get that consistent force that we need. And then more importantly, when it comes to tool design, is understand that that might happen. And so let's make these tools and design them to be as serviceable as possible, because as I'm sure we can all attest, uptime is critical. So if it's going to happen, let's make sure that the effects are not going to be detrimental. Let's minimize the effects and make sure that we can recover quickly as possible.
Thank you, Dan. Sarah, this next question is for you. Is there a difference in friction force between new and worn out abrasive belts, and how are these two parameters connected?
I'm sorry, can you repeat that?
Sure. Is there a difference in friction force between new and worn out abrasive belts, and how are these two parameters connected?
I think that if I understand the question that is being asked, the force you need is going to change across the use of a belt. So if you are in a coated belt, because you're going to be breaking down that grit, and over the course of use, you're going to have more force. You're going to have more surface area on the tips of those grits than you did when they were all perfectly sharp at the very beginning. So we do, one way that this is addressed in order to keep a consistent performance, because hopefully, and typically you're going to do many parts on one belt. So one way to address that is at the system integrator, they can make the controls such that you have zones. And again, back to that empirical life measurements that I was talking about, you can observe on your parts, see when the cut rate is slowing down a little, and basically make a zone or select a different force zone that increases the force to get it back into the optimal range. So this is actually one of the coolest things about robotic abrasive processes, is that there's a lot of ways to solve the problem. So this is one where working with a system integrator and what their tools are for running the controls on the machine and the programming on the machine, and our knowledge about the performance curve on the abrasive product and how that manifests visually on the part when it's changing. You bring those two together and we can make some powerful solutions for the customer.
Thank you, Sarah. Our next question is for the both of you. So Dan, we'll start with you and we'll go to Sarah. How do you know what is best, if the robot holds the part or the tool to remove material?
I'm sorry, Clarissa, could you repeat it? The first part of the question didn't come through.
Sure. How do you know what is best, if the robot holds the part or the tool to remove material?
Well, that's an excellent question. And the good news is that one way is not necessarily better than the other. We call that part in hand or part to process, where the robot actually has a gripper or some other means to hold the part and present it to the material removal process. The other option is what we call process to part, where a lot of those photos we saw, we have the actual material removal tool on the robot, and that is being articulated around a fixed part. The benefits of that compliance and force control apply either way. So either way, that range of motion and forgiveness, that consistent applied force is going to achieve our goals. Now, which one you choose is going to be based on the type of part, the size of the part, and all of those other automation considerations. For instance, if we want a robot to pick a part out of a bin, then we already have a gripper or an end effector that can do that. So we might lean towards a part to process operation. If it's coming in on a conveyor and it's already located, we might then start with a process to part. So it depends on what else is going on upstream and downstream. What are our constraints? If the part is extremely heavy, right? We saw in the video game controller active force control application, those were really, really large, heavy castings, and we're doing gate removal in that application, and so it's really hard to locate that part. And so in that case, it wouldn't make much sense to grip that gigantic part and then articulate it around. So we have to understand the robot kinematics and the rest of our environmental factors combined with that upstream and downstream consideration to choose which one might be better for our situation.
Yeah, I'll just add that one of the factors, this is where that robot reach can actually be really important, and how the integrator is actually designing spatially the layout in the cell. Sometimes, depending on your part, that may lean you one way or the other, that it's easier to maneuver. It's easier for the robot to maneuver the tool versus the part, or vice versa. And, they're the ones who are experts on visualizing and simulating the robot reach with your part in hand, right? Another factor is equipment. So we've kind of referred to this a couple of times. There are more tools out there than you see conventionally in manual operations. So whatever your vision of a conventional belt back stand is not typically what's used in a robot cell. So many system integrators will either design their own belt stands so that they can take into account that the spatial requirements, or they will turn to somebody who makes equipment specifically for robotic use. So it is, I think, a really good example of why our proof of concept with you isn't the end of designing your abrasive process, because there may be something later in the design process that asks the question, are we constrained here? Do we have to hold the part? Can we flip this around? Do we need flexibility? Do we have flexibility? And it's totally normal, and we come up with solutions all the time.
Thank you, guys. And this will be our last question. Sarah, we'll start with you, and then we'll go to Dan. If my process is 100% manual, or I have an application for robotic finishing, deburring, or grinding, where do I begin?
Well, I hope if you take one takeaway from this, it's come and talk to your abrasive experts early. I would definitely start with reaching out to us about what you hope to do, and I hope that we have conveyed that this field is actually, it's a network of companies who all know we have to work together in order to create successful cells. So if you, whether you come to us and say, here's what we want to do, and it's a really similar to things we've seen before, so we don't have to do much process work. Maybe you want to get connected with an integrator, or you have some questions you want to ask. What kind of questions should I be asking an integrator? One resource we have is our www.3m.com/robotics. We have a bunch of questions that you can use to help get yourself ready to talk to a system integrator. So I think that's really the place to start. Often it's with a phone call, and we can also bring in, once we understand what your problem is, we can bring in further application engineering experts in that application area as needed, and partners like ATI and robot companies and integrators.
Yeah, I would agree. And of course, it's a little self-serving, but we really do think involve us early and let us help you ask those questions. It's really common for end users to come to us directly after a Google search or seeing a YouTube video. And, it's just like, here's our manual process. What can I do? And so congratulations. First of all, you've considered automation. You've identified an opportunity. You're looking for value of automation. And so let us help to shortcut it. It's this giant funnel of potential solutions, so it's a little overwhelming. What we can do, 3M and ATI, is use our experience and say, okay, you're doing aluminum deburring, or you're doing gate grinding on an iron casting. Here are some similar applications. We might have information that we can share, or a case study, maybe even photos or videos of past applications that have been successful. So let us help you early to try to narrow that down a little bit. And then as you get more and more investment, as you get more and more, buy-in from either your customer, if you're an integrator, or if you're an end user from your CapEx approvers, we can help to shortcut that process with the proof of concept. That's where things really start to take shape. So we can help you early to try to narrow it down, and then we can do that proof of concept to make sure that we're not going to be designing the cell for you at ATI, but what we can do is say, here's what's possible with a robot and with this tool or with this process. And then we do have industry partners, obviously 3M, but then a tremendous network of integrators who, if you need some help, if you don't have any robots, we can put you in touch with people that might be local to you, or maybe have the best expertise based on their experience and your needs.
Thank you. Thank you to Dan and Sarah, and to those who submitted questions. This concludes the question and answer portion of today's webinar. If we didn't address your question live, we will respond via email. Please join us for the next webinar in our A3 series being held after Vision Week on May 28th, titled EtherCAT as a Master Machine Control Tool. We'll discuss how to utilize EtherCAT Masters for high-performance machine control, while covering all areas of automation, motion control, safety, and measurement. Register for free on the RIA, AIA, or MCMA webinar pages. I hope you found this webinar to be interesting and informative. If you have any questions about the Association for Advancing Automation or today's webinar, please reach out to either Dan, Sarah, or myself via the contact information you see on the screen. As a reminder, this webinar has been recorded, and an email with a link to the recording will be sent to you in the next 24 hours. Thank you again to Sarah and Dan for presenting, ATI for their sponsorship, and to all of our listeners for your support. Stay safe and healthy, and have a wonderful day.